Okay, this is Physics, Chapter 6, Force Problems. These are the practice problems, key to success for the Chapter 6 test. Let's go over these solutions real quick. I tried to model a lot more detail than you need to show, but at least stuff that you need to show me on the test that you're thinking about and going through. Step number 1, free body diagram. Step number 2, use my free body diagram, and I use Newton's law with all forces perpendicular to solve for force normal. Step number 3, use Newton's law for all parallel forces and solve for your unknown, regardless of what it is. Step number 1, free body diagram. Remember, every single one of these forces, and there's only 4 of them, you need to think, does it exist? What's its direction? What's its magnitude? Force of gravity, no brainer, always exists, always straight down. Magnitude is always m times your gravitational acceleration constant. In these problems, that is the only thing that you use little g in. These are not free fall problems. Nothing is accelerating at 9.81 unless it's in free fall. All right, all these other ones, force normal, does it exist? If there's a plane of contact, I'm sliding along the floor, plane of contact, then force normal exists perpendicular to the plane. What's its magnitude? We'll find out right here. Since I'm in equilibrium in the vertical dimension, this is going to have the same magnitude, right? We go into infinite detail right here to prove that. All right, force applied, given. Force of friction, remember this thing is actually sliding. This is going to be a constant that I can compute. That is not the force of friction, that is the coefficient of friction. I multiply that by force normal, right? So I can get its magnitude. Now I'm ready for Newton's second law in this dimension, compute my unknown. There we are, F net for all my forces parallel. All right, now the next 2 problems are just a spin-off. All right, what I'm telling you now is what, same scenario, same box, same weight, same force normal, but now I'm trying to get how much force to get the box moving. It's not quite moving yet, so I am in equilibrium. All right, but I'm going to have to overcome this static force. Remember what we did in the lab. All right, we had this force of static friction, and it reaches some maximum. It goes up, up, up. So Fs is constantly going up until I reach a maximum threshold, and then boom. And now all of a sudden, force of friction kinetic or dynamic is a constant. All right, so I need to get a force greater than 460 newtons to get this thing actually moving. And now what is it to keep it moving? All right, I'm now in this area of my force friction. I'm still in equilibrium. So since I'm moving at constant velocity, this and this are going to be in equilibrium. So if I learn what this value is, then I know by process of deduction what this value is. All right, so if you'll notice, this front page is all some sort of spin-off of what we did in the lab. Okay, let's talk about this one. Now, this one is a little bit confusing. First of all, this is a mu static situation. Right here, I am kind of stuck on the snow. I need to know this force applied to break this static friction. So I'm going to use mu s force normal and calculate then what this is to get me moving. All right, so then I'm chugging along and I let go of the rope. Now I'm in a dynamic problem. I had this velocity of 3 meters per second, and I'm going to slow down to a stop. That means my acceleration is this direction. That means I need an F net in the direction. So how does my free body diagram change? Well, this goes away, And it is only the sliding force of friction that's going to bring us to the stop. Since I'm actually moving, this now drops from US to mu K, and here's my free body diagram, not in equilibrium, but an F net in this direction. So I can go to Newton's second law, solve for my acceleration. I'm going to use that acceleration then in some kinematics data to find the distance that I moved. All right, I've changed the wording of this problem. This should say as you jump off a wagon, meaning that the boy and the wagon are still in contact, which means it's going to be a third law problem. Now, I know the mass of you, and I know your velocity, your acceleration, so I can calculate the force. So the boy has this much acceleration, this much mass, so this is the force acting on the boy to accelerate him in this direction. Well, that has to, by Newton's third law, be equal and opposite to the force of the wagon. So this is just like a tug-of-war problem, really, except I'm pushing instead of pulling. The principle is exactly the same. This amount of force is acting on the wagon. I know the mass of the wagon, therefore I can compute the acceleration of the wagon. All right, we'll have to continue this in the next video. Getting a little long here. Okay, what people want to tell me is they want to tell me that this force of tension in the bale is 118. If this was an equilibrium, that would be true, but it's not. We're accelerating. So that means this has to be bigger than that. Going to Newton's third law, I'm going to call force of tension positive, weight negative. This is F net then, mass times acceleration. I can back compute the force of tension. All right, and then we're given the acceleration and some other kinematics data, so I can compute this V final. All right, think back to the elevator lab. What does this tell me? This tells me that I'm going to have an acceleration in this direction. So to get an acceleration in that direction, think of the vector dance. Something getting faster if my velocity was in this direction. Something getting slower if my velocity was in this direction. So this gives me two scenarios. I can be going down and speeding up, or I can be up and slowing down. All right, this is getting a little bit too long. I'll continue this last page in another video. Thanks.